Yes, good afternoon, everyone. Welcome to the another session on engineering mathematics 4. In the yesterday's class, we have seen the definition of Fourier transform. Fourier transform, and already we have seen the Fourier definition of Fourier transform and some related problems here. Yesterday, we have seen the definition of Fourier sine and cosine transform. That will be the infinite Fourier sine and cosine transform. That type of idea. Infinite Fourier sine and cosine transform. That type of idea. We have seen that, and the related properties also we have concluded here, in which we have one Parseval certainty. That property is very important property considering the problems here. So we'll see today some problems related to Fourier sine and cosine transform ideas here. Fourier sine and cosine transform ideas that we'll see today. We take our first problem here. Problem number 1. Find the Fourier sine transform and the Fourier cosine transform of. Find the Fourier sine transform and the cosine transform of. Find the Fourier sine and the cosine transform of f of x equal to e power minus ax. F of x equal to e power minus ax. E power minus ax. A greater than 0. E power minus ax. A greater than 0. Find their respective inversion formulae. Find their respective inversion formulae. Find their respective inversion formulae. And evaluate the following integrals. And evaluate the following integrals. And evaluate the following integrals. For 1, integral 0 to infinity, integral 0 to infinity, dx by x square plus a square whole square, x square plus a square whole square. Number 2, subdivision number 2, integral 0 to infinity, integral 0 to infinity, x square dx whole divided by x square plus a square whole square, x square dx whole divided by x square plus a square whole square. Number 3, integral 0 to infinity, integral 0 to infinity, dx by x square plus a square into x square plus b square, square plus a square into x square plus b square. Subdivision number 4, integral 0 to infinity, x square dx whole divided by square dx whole divided by x square plus a square into x square plus b square, square plus a square into x square plus b square. And all the 4 subdivisions, a comma b values are greater than 0. A comma b is greater than 0. In all the 4 subdivisions, a comma b values are greater than 0. Okay? Right. Now we are going to identify, first of all, Fourier sine and cosine transform f of x equal to e power minus ax. Correspondingly, their inversion formulas here. Based on that, we can deduce these 4 integrals values. 4 integrals values. First, find f of x Fourier sine and cosine transform. Given f of x equal to e power minus ax, a greater than 0. Given f of x equal to e power minus ax, a greater than 0. First, find Fourier sine transform. By definition, FSI f of x equal to FSI f of x equal to root of 2 pi pi. You know the definition, 0 to infinity. Where sine transform will be f of x sin sx dx. F of x sin sx dx. That is equal to fs of s. That is equal to fs of s. Right. Now instead of f of x here, e power minus ax, fsi e power minus ax equal to root of 2 pi pi integral 0 to infinity e power minus ax sin sx dx. Root of 2 pi pi integral 0 to infinity e power minus ax sin sx dx. Sin sx dx. You know the formula for e power ax sin bx dx. E power integral e power ax sin bx dx is equal to e power ax by a square plus b square a sin bx minus b cos bx. A sin bx minus b cos bx. For here, instead of a minus a, instead of b is s. Therefore, e power minus ax by root of 2 pi pi or minus ax by minus of a whole square plus s square minus a square plus s square into minus a sin sx because a is minus a sin sx. Then formula minus here b cos bx, here b is s cos sx, s cos sx minus s cos sx 0 to infinity. 0 to infinity. That is equal to root of 2 pi pi e power minus infinity 0, e power minus infinity 0 minus 1 divided by s square plus a square, s square plus a square. And applying infinity here, 0. When applying 0, e power 0, 1 by s square plus a square. Applying 0 here, sin 0, 0, cos 0, 1, or minus s you can get. Minus. So totally your answer will be minus minus plus here, root of 2 pi pi s by s square plus a square. Root of 2 pi pi s by s square plus a square, that is equal to fs of s. This will be Fourier sine transform. We can take fs of s. Now using this obtained result, fs of s, we can use inverse Fourier transform because they are asking inversion formula. Therefore, we can use inverse Fourier sine transform definition. We can get some idea. I can get some relations. Can I move into next page? Next page. By inverse Fourier sine transform, we have. By inverse Fourier sine transform, we have. What do you have? F of x can be written as f of x equal to root of 2 pi pi, integral 0 to infinity, fs of s sin sx ds. Fs of s sin sx ds. Everything, yes, function of s. Now f of x equal to here e power minus ax. F of x equal to e power minus ax. Root of 2 pi pi, integral 0 to infinity. Fs of s is just now we have time. Here root of 2 pi pi s by s square plus a square. Root of 2 pi pi s by s square plus a square. It will be sin sx ds. It will be 2 pi pi integral 0 to infinity s by s square plus a square sin sx ds. Okay. This is your integral formula using inverse Fourier sine transform. Okay. And then these two are constant. Take it right side, left side here. Then integral 0 to infinity with respect to s here. Yes. Everything is s here. Therefore, s by s square plus a square sin sx ds is equal to pi by 2 e power minus ax. Pi by 2 e power minus ax. A is greater than 0. Pi by 2 e power minus ax. A is greater than 0. Okay. Okay. This is one inversion formula. Similarly, you can use Fourier cosine transform definition for f of x equal to e power minus ax. Similarly, by Fourier cosine transform definition, FCI f of x is equal to root of 2 pi pi integral 0 to infinity f of x cos sx dx, the 0 to infinity f of x cos sx dx for cosine transform, that's equal to FCFS. Yeah, you know the definition of Fourier cosine transform here. For FCI e power minus ax, instead of f of x here, we put e power minus ax, e power minus root of 2 pi integral 0 to infinity e power minus ax cos sx dx, e power minus ax cos sx dx. Then you know the formula for e power ax cos bx dx. Even though e power ax cos bx dx is equal to e power ax by a square plus b square. Everything is plus a cos bx plus b sin bx. For sin only you can get minus here. Sin starts with sin and here cos. But here cos start with cos, here sin. But both are plus a cos bx plus b sin bx. Or you can use the formula root of 2 pi 0 to infinity e power minus ax by a square plus s square b is s minus a cos sx plus s sin sx. No, s sin sx. Root of 2 pi when applying infinity e power minus infinity 0. E power minus infinity 0. When applying 0 here, e power 0 1, 1 by s square plus a square. Applying 0 cos 0 1, sin 0 0 here. Therefore minus a plus 0. Minus minus plus, therefore you can write it as root of 2 pi a by s square plus a square. A by s square plus a square. That is equal to fc of yes. That is equal to fc of yes. So this is Fourier cosine transform e power minus ax. Fourier cosine transform e power minus ax. That is equal to root of 2 pi a by s square plus a square. A by s square plus a square. Okay, right. This page over.
Yes, sir.
Okay. Then we can use inverse Fourier cosine transform. With that further we can reduce one formula. By inverse Fourier cosine transform, we have f of x equal to root of 2 pi integral 0 to infinity fc of s cos sx ds. fc of s cos sx ds. F of x equal to root of 2 pi 0 to infinity fc of s cos sx ds. F of x is e power minus ax root of 2 pi 0 to infinity. fc of s just now we have completed root of 2 pi a by s square plus a square. Root of 2 pi a by s square plus a square cos sx ds. Cos sx for e power minus ax 2 pi it is 2 pi a is constant, take it outside here. 0 to infinity cos sx by s square plus a square. Cos sx by s square plus a square ds. Cos x by s square plus a square ds. So this is the formula we are getting here. Del 0 to infinity cos x by s square plus a square ds. Del 0 to infinity cos x by s square plus a square ds here. These are constant, take it right side, left side here. It will be pi by 2a e power minus ax, a greater than 0. Pi by 2a e power minus ax, a is greater than 0. It is another relation. Del 0 to infinity cos x by s square plus a square ds. Okay, right. Now these are the inversion formula we are getting here. Okay? And further, what are the things we have to identify? You see the question here. Find the Fourier sine and cosine transform f of x equal to e power minus ax, a greater than 0. Find the respective inversion formula. The for respective inversion formula just now you have completed. And now you have to evaluate these four integrals. Okay, right. You see the four integrals here, x square plus a square whole square form, and correspondingly on x square is multiplied here constant, and here x square by the same function. Same one. Similarly here constant product of two functions x square plus a square, x square plus b square. Similarly the same function in the denominator, but numerator on x square. Same denominator first to two, and numerator is x square. Here is also same denominator, and numerator is x square. Now you have to evaluate this integral. Now see that what are the Fourier sine and cosine transform of f of x equal to e power minus x, that you have to remember once again. Fourier sine transform is root of 2 pi pi s by s square plus s by s square plus a square. Okay. Now you see the denominator here s square plus a square, the deduction integral also s square plus a square, here x square plus a square. But deduction here s is also there, here s is also. Therefore if you square this one, you can get s square by s square plus a square, s square by s square plus a square whole square. If you square fs of s, if you square fs of s. For squaring fs of s, where you can identify, what type of property you can use? Squaring fs of s, what property you can use? Can anyone have the idea? Squaring fs of s, and also that is inside the integration, squaring fs of s, and also inside
Parseval's identity.
Parseval's identity. But we can use Parseval's identity here. Okay? Fs of s square, Parseval's identity. That Parseval's identity of fs of s square, that gives the second integral. Okay? That gives the second integral, this integral. Similarly, this first integral is constant in the numerator. Okay? Numerator is constant. Or if you see the Fourier cosine transform, your answer will be fc of s is constant in the numerator. Therefore 1 by s square plus a square only. Okay? 1 by s square plus a square. Squaring this one, you can get 1 by s square plus a square whole square, you can get here. 1 by s square plus a square whole square. And this is 1 by s square plus a square whole square. And you can replace s by x square. Or if you use Fourier cosine transform Parseval's identity, you can get first integral. If you use Fourier sine transform Parseval's identity, you can get second integral. Second integral. Therefore, you can use Parseval's identity first now here. Now to evaluate the four integrals, deductions. You put deductions. First one, integral 0 to infinity dx by x square plus a square whole square. Integral 0 to infinity dx by x square plus a square whole square. Integral 0 to infinity dx by x square plus a square whole square. Therefore, constant in the numerator means you can use Fourier cosine transform of e power minus ax. Fourier cosine transform of e power minus ax. Therefore, you can use Parseval's identity. We know that Parseval's identity. We know that by Parseval's identity that integral 0 to infinity mod f of x square dx, Parseval's identity of Fourier cosine transform. Integral 0 to infinity mod f of x square dx is equal to integral 0 to infinity mod fc of x square ds. Mod fc of x square ds. For f of x is e power minus ax, therefore integral 0 to infinity mod e power minus ax square dx, that is equal to integral 0 to infinity. Corresponding fc of s, already you know that fc of s is here root of 2 pi pi a by s square plus a square. Root of 2 pi pi a by s square plus a square. Therefore, we can use root of 2 pi pi a by s square plus a square whole square ds. Okay? Whole square ds. Now modulus square, but inside function is real function. It is also real function. Modulus square is nothing but ordinary square. Okay? Modulus square is nothing but ordinary square only. Therefore, ordinary square means you can get e power minus 2ax. Here 2 pi pi a square. A square, take it outside here. Okay? A square. Ordinary square, therefore integral 0 to infinity e power minus 2ax dx. E power minus 2ax dx. 2 pi pi a square, take it outside here. 0 to infinity ds by s square plus a square whole square here. Because ds by s square, only real function. So we can get ds by s square plus a square whole square. Ds by s square plus a square whole square. E power minus 2x by minus 2a integration 0 to infinity 2a square by pi equals 0 to infinity ds by a square plus a square whole square. Integrate left side part only, right side is as it is only. Minus 1 by 2a integrate e power minus infinity 0 e power 0 1 was 0 minus 1. So 2a square by pi integral 0 to infinity ds by s square plus a square whole square. This is plus 1 by 2a. This integral value only we require for integral 0 to infinity ds by s square plus a square whole square, that is equal to, we cross multiply, this is 1 by 2a, multiply here 4a cube pi by 4a cube. Then convert with the general variable instead of s, x here, s by x here, therefore 0 to infinity dx by x square plus a square whole square, 0 to infinity dx by x square plus a square whole square equal to pi by 4a cube, pi by 4a cube, a greater than 0. Okay. So this is your answer. And the second subdivision, they are asking x square by x square plus a square whole square here, second subdivision. Therefore, you have to use Parseval's identity of Fourier sine transform. Parseval's identity of Fourier sine transform. Fourier sine transform. For the second one, use Parseval's identity of Fourier sine transform. Integral 0 to infinity x square dx by x square plus a square whole square. X square dx by x square plus a square whole square. For that, you have to use Parseval's identity of Fourier sine transform. Because sine transform only, a sine transform of e power minus ax only, s in the numerator. So you can use that idea. And 0 to infinity mod f of x square dx is equal to 0 to infinity mod fs of s square ds by Parseval's identity. And that can be written as 0 to infinity modulus of e power minus ax square dx equal to 0 to infinity fs of s. Just we already know that modulus fs of s is equal to root of 2 pi by s by s square plus a square, s by s square plus a square, root of 2 pi by s by s square plus a square ds. 0 to infinity e power minus 2ax dx, 0 to infinity e power minus 2ax dx, that is equal to 2 pi pi be s square by s square plus a square square, s square by s square plus a square square ds. Okay. Because everything is real function, will be ordinary square only. Ordinary square only. Then integrate here. If you integrate this one, you see the left side integration is, can you give the answer for the integration? After this, can you proceed further?
Integral of 0 to infinity
Hmm.
x square by x square plus a square the whole square into
Ah,
dx
ah,
is equal to pi by 4a.
very good, very good. Equal to pi by 4e. So your answer will be pi by 4e. Pi by 4e. Okay? Is good. X square by x square dx by x square plus a square. Your answer will be pi by 4a. pi by 4. Third subdivision, they are asking that third and fourth, you see that here, dx by x square plus a square, x square plus b square. Numerator is constant, means you can use Fourier cosine transform e power minus 6. Numerator is x means you can use s or x square means you can use Fourier sine transform e power minus 8. Now you see that previously x square plus a square, here x square plus a square, but one more function x square plus b square is present, and therefore you can use the
f of x, g of x.
f of x, g of x, that property. Because Parseval's identity derived Parseval's identity from that property only, or you can use that one. Or you take two functions here, f of x as a e power minus ax, a greater than 0, and g of x as a e power minus bx, b greater than 0. You know the property that integral 0 to infinity f of x g of x dx is equal to, by property 5, integral 0 to infinity fc of s gc of s ds. Fc of s gc of s, that property you can adopt. For that purpose, you take f of x equal to e power minus ax a greater than 0, and g of x as a e power minus bx b greater than 0. Because numerator is constant, first find Fourier cosine transform. Fourier cosine transform f of x is equal to root of 2 pi pi a by s square plus a square. Root of 2 pi pi a by s square plus a square. Already you know the result. That will be fc of s. You take it because fc f of x is fc of s. Similarly, for g of x, Fourier cosine transform is Fourier cosine transform g of x is equal to root of 2 pi pi b by s square plus b square. B by s square plus b square equal to gc of s. Gc of s. Now you know the property. We know that property 5, by property 5. Integral 0 to infinity f of x g of x dx. F of x g of x. Integral 0 to infinity f of x g of x dx equal to 0 to infinity fc of s gc of s ds. Therefore, substitute f of x g of x. F of x is e power minus ax. G of x is e power minus bx dx. Integral 0 to infinity fc of s is root of 2 pi by a by s square plus a square. B root of 2 pi by b by s square plus b square. Integral 0 to infinity e power minus of a plus b x dx. Right side is wherever constant, you take it outside here. 2 pi root of 2 pi by 2 pi pi a b, you take it outside. Then integral 0 to infinity ds by s square plus a square, s square plus b square. Okay. Integrate left side e power minus I a plus b x whole divided by minus I a plus b 0 to infinity 2ab by 5 equals 0 to infinity ds by s square plus a square, s square plus b square. Okay. Right. And substitute limits e power minus infinity 0, e power 0 1, therefore minus 1 by a plus b, you take it outside here. Minus 1 by a plus b, take it outside. 0 and 1, minus 1, 0 and minus 1. Right side is 2aq by sorry, right side is 2ab by p, so on, same thing. 2ab by b, 2ab by pi equals 0 to infinity, so on. We require this integral value 1 plus 0 to infinity ds by s square plus a square. Cross multiply, minus minus plus, working at pi by 2ab into a plus, pi by 2ab into a plus. Numerator change it by s by x here, s by x. 1 plus 0 to infinity dx by x square plus a square, x square plus b square equal to pi by 2ab into a plus, pi by 2ab into a plus b. Correct? Right. The same manner, for fourth one, can use this formula again. This one. The 0 to infinity f of x g of x dx property. F of x g of x dx equal to 0 to infinity fs of x gs of x. Fourth one, you have to identify the value of the integral 0 to infinity x square dx by x square plus a square, x square plus b square, square plus a square, x square plus b square. For that, again take it as f of x equal to e power minus x. You have to use Fourier sine transform. Fourier sine transform. For f of x equal to e power minus ax, a greater than 0, and g of x equal to e power minus bx, b greater than 0. Correspondingly, it's their Fourier sine transform. Fs f of x equal to root of 2 pi pi s by s square plus a square fs of s. S by s square plus a square fs of. This is fs of s. S in the numerator. There is also fs of g of x. That is called gs of s. Function g is Fourier sine transform. Gs of s. Root of 2 pi by s square plus b square. And we know that the 0 to infinity f of x g of s gs is equal to 0 to infinity fs of s gs of s ds. Gs of s. G of x dx equal to 0 to infinity fs of s gs of s. Can you proceed further and give your answer? Substitute f of x, g of x, and fs of s, gs of s. Substitute f of s, g of s, fs of s, g of s, gs of s. What about your answer? What about your answer?
Pi by 2 into a plus.
Okay. Pi by 2 into a plus b. Okay, your answer will be pi by 2 into a plus b. Therefore, your answer will be 0 to infinity x square dx by x square plus a square, x square plus b square. If we change s by x, s by x, we can get pi by 2 into a plus b. Pi by 2 into a plus b. These four integrals you might be solved in the third semester using contour integration. Contour integration type 2 procedure. These four integrals it might be solved with the help of contour integration techniques here of type 2 polynomial type here. Is these integrals can be solved with the help of either contour integration or Fourier transform techniques. Only these two types are possible. These two types are possible. Other types, another way, it will be very difficult to identify the value of the integrations. Value of the integration. Therefore, only Fourier transform techniques or contour integration, complex integration techniques will be used to solve that solution of these four integrals. This four. So this problem is very important, and at least one deduction you can expect definitely here. For if denominator is like this type of polynomial, you remember this function. Suppose they are asking directly evaluate these integrals using Fourier transform technique, means you remember this function f of x equal to e power minus ax, then proceed sine and cosine transform. With the help of that, we can finish the solution value of the integration. Value of the integration. So this is very important problem. All of you getting the same answer for this problem? Same answer. Okay. Next, one more problem. Find the Fourier sine and cosine transform of. Find the Fourier sine transform and Fourier cosine transform of x power n minus 1. X power n minus 1. And hence prove that 1 by root x is self-reciprocal under Fourier sine transform and Fourier cosine transform. 1 by root x is self-reciprocal under Fourier sine transform and Fourier cosine transform. Fourier cosine transform. We have to identify Fourier sine and cosine transform x power n minus 1. Fourier sine and cosine of x power n minus 1. You have to proceed further. Further, you have to show that 1 by root x is self-reciprocal under Fourier sine and cosine. Suppose if you use the definition directly here, integral 0 to infinity, integral 0 to infinity, x power n minus 1 Fourier sine or cosine transform. I can use integral x power n minus 1 cos sx, cos sx dx, cos sx dx, that type of things you can follow here. But root of 2 pi by before that, root of 2 pi by, root of 2 pi by you can use before that here. Then we can proceed further. X power n minus 1 cos sx dx, that thing you can follow here. But if you, it is a product of two functions here, product of two functions here, x power n minus 1 cos sx. If you use integration by parts or Bernoulli's formula here, this is u, this is v, means you have to, because of x power n minus 1, you have to proceed for n minus 1 derivatives, u dash, u double dash, up to n minus 1 derivatives you have to proceed. Then only you can get constant. Or you don't know what is the value of n, for proceeding up to n minus 1 derivatives, and we cannot, you cannot identify that where we have to stop here. This will be, you don't know what is the exact value of n, therefore you cannot stop, and where you get to get the relations, that type of thing very tedious. So instead of moving by this way, this x power n minus 1 and cos sx can be written with the help of e power isx, e power isx. Therefore, x power n minus 1, 0 to infinity exponential negative minus isx or negative, that can be getting with the help of gamma integral result. Gamma integral, because x power n minus 1, 0 to infinity negative exponential, immediately we have to think about gamma integral. So you know gamma integral result. So take it here, f of x power n minus 1, f of x power n minus 1, and you know gamma integral result here, integral 0 to infinity e power minus ax x power n minus 1 dx. Integral 0 to infinity e power minus ax x power n minus 1 dx equal to gamma n by a power n. Gamma n. Simply gamma n means 0 to infinity e power minus x power n minus 1. E power minus x power n minus 1. This is gamma n. Instead of x, ax is there, means you put ax equal to y. You can get this extra additional a power n in the denominator, like a gamma integral result. Or in the above result, put a equal to is. Put a equal to is. Is. Why you are not solving this problem with the help of direct definition? You are using gamma integral because x power n minus 1 time is present. Put a equal to is e power minus isx x power n minus 1 dx here. Here a equal to is here, gamma n by is power n. Now write this is as isx as a e power minus isx as a cos sx minus I sin sx. And the 0 to infinity x power n minus 1 as it is here, x power n minus 1 as it is. This is a cos sx minus I sin sx dx. Right side is, right side is 1 by I power n gamma n by s power n. 1 by I power n gamma n by s power n. We split these two integrals here, cos sx and then minus I sin sx here. Therefore, 0 to infinity x power n minus 1 cos sx minus I sin. Left side integral is a real and imaginary part. Right side is also imaginary thing is present, but you have to write as a purely real and imaginary part. Purely real and imaginary part. For that purpose, you write 1 by I power n as a 1 by I whole power n. 1 power n by I power n. 1 power n by I power n. Write it like a 1 by I whole power n. Gamma n by s power n. 1 by I generally written as minus I. Minus I. Now this minus I can also be, because minus I power n, you have to get this I n inside here. For that purpose, this I can be written as 0 minus I minus I sorry minus I into 1 minus I into 1 and whole power n form, whole power n form. This minus I can be written as 0 minus I into 0 minus I into 1 whole power n. Now this 0 can be written as cos pi by 2, cos pi by 2 minus I sin pi by 2, minus I sin pi by 2 whole power n. Cos pi by 2 minus I, this 1 can be written as sin pi by 2 power n, gamma n by s power n. In order to get that n inside condition, for that purpose write it like a cos theta minus I sin theta power n. Now it is like a De Moivre's rule you can apply. Cos theta minus I sin theta whole power n equal to cos n theta minus I sin n theta. So cos n pi by 2 minus I sin n pi by 2 gamma n by s power n. Yes. Now it is in the perfect form, real and imaginary. Left side is also real, imaginary, real, imaginary. Therefore equate real and imaginary parts both sides. Equate real and imaginary part both sides. This is real part, it is imaginary part. Here is also minus I, here is also minus I. For both the imaginary part minus I, remaining thing you can get. For equate real and imaginary parts both sides, equate real and imaginary parts both sides, what you can get here. Del 0 to infinity x power n minus 1 cos sx dx. Del 0 to infinity x power n minus 1 cos sx dx equal to cos n pi by 2 gamma n by s power n. Cos n pi by 2 gamma n by s power n. And similarly here minus I, therefore both are plus here. X power n minus 1 sin sx dx equal to gamma n by s power n sin n by b2. 0 to infinity x power n minus 1 sin sx dx equal to gamma n by s power n sin n pi by 2. Right. Both are seems like a Fourier cosine transform. This is Fourier sine transform. If you multiply by root of 2 pi by both sides, if you multiply by root of 2 pi by, it definitely it will be a definition of Fourier cosine, Fourier sine. Or multiply both sides by root of 2 pi by for the first one. Root of 2 pi by 0 to infinity x power n minus 1 cos sx dx is equal to, here is also multiply by root of 2 pi by, root of 2 pi by gamma n by s power n cos n pi by 2, gamma n by s power n cos n pi by 2, and here is also multiply by root of 2 pi by root of 2 pi by 0 to infinity x power n minus 1 sin sx dx is equal to, sin sx dx is equal to, here is also multiply by root of 2 pi by and so on. Wow. What is this? This is the Fourier cosine transform x power n minus 1. This is Fourier sine transform x power n minus 1. So that's all. That will be your answer. Right? This page over. This page over.
Yes, sir.
Yes. Okay. Therefore, this is Fourier cosine transform x power n minus 1. That's equal to root of 2 pi pi gamma n by s power n cos n pi by 2. Similarly, Fourier sine transform x power n minus 1 equal to root of 2 pi pi gamma n by s power n sin n pi by 2. Gamma n by s power n sin n pi by 2. Sin n pi by 2. Therefore, instead of using direct definition, can use gamma integral idea, gamma integral definition. With the help of that, we are identifying Fourier sine and cosine transform of x power n minus 1. Fourier sine and cosine transform of x power n minus 1. Okay. You see the deduction here. What is the deduction they are asking you? 1 by root x is self-reciprocal under Fourier sine and cosine. 1 by root x means x power minus 1 by 2. X power minus 1 by 2. Fourier sine and cosine as x power n minus 1 by 2. Therefore, for that you put n equal to 1 by 2. N equal to 1 by 2 means x power minus 1 by 2 you can get. Or the deduction put n is equal to 1 by 2. N equal to 1 by 2 in the above result. Put n equal to 1 by 2 in the above result. You get Fourier cosine transform 1 by 2 minus 1 root r 2 pi pi. It is n equal to 1 by 2 gamma 1 by 2 s power 1 by 2 1 by 2 1 by 2 pi by 2 n equal to 1 by. Similarly, sine transform also the same thing. Okay? Sine transform also the same thing. This is sine transform. Fourier fs of x power 1 by 2 minus 1 equal to root r 2 pi pi gamma 1 by 2 by x power 1 by 2 and so on. Everyone know that gamma 1 by 2 value equal to root of pi, square root of pi. But this gamma 1 by 2 root pi get cancelled. There is also gamma 1 by 2 root pi get cancelled. What about left side here? Left side is fc of x power minus 1 by 2. That's 1 by root x. Okay. And root 2 by s power of cos pi by 4. This is cos pi by 4. And here is also fs of 1 by root x. Fs of 1 by root x equal to root 2 s power 1 by 2 root 2 by s power 1 by 2 sine pi by 4. Sine pi by 4. Because everyone know that gamma 1 by 2 equal to root pi. And also you know that cos pi by 4 values, sine pi by 4 values are 1 by root 2. 1 by root 2. Suppose that root 2 also get cancelled. Root 2 also get cancelled. Also you know that cos pi by 4 equal to sine pi by 4 equal to 1 by root 2. 1 by root 2. With the help of that, you can say that fc of 1 by root x equal to 1 by root s. Fs of 1 by root x equal to 1 by root s. It means that you are getting the same function after transformation. After transformation of this function into cosine transform, delta cosine transform, they are getting the same function. Here is also the same thing. Fs of 1 by root x also 1 by root s. Fs of 1 by root x also 1 by root x. Therefore, 1 by root x is self-reciprocal under Fourier sine and cosine transform. 1 by root x is self-reciprocal under Fourier sine and cosine transform. Okay, because transform of the function is itself. Only variable only changed, but function is same function. Transform of the function is itself, and you can say it will be a self-reciprocal function. Okay? 1 by root x is self-reciprocal under Fourier sine and cosine transform. 1 by root x is self-reciprocal under Fourier sine and cosine transform. Okay. Just put n is equal to 1 by 2. N is equal to 1 by 2 in the obtained result. And you can get all the required deduction. This problem is also very, very important. Here you are not using the definition directly, because it may go up to n minus 1 derivatives here. Instead of moving that way, you can get this idea. Obviously, gamma n also n minus 1 factorial. N minus 1 factorial. If you differentiate n minus 1 time, n minus 1 x power n minus 2, n minus 2 x power n minus 3, it moves like that here. Then finally it ends with 2, 3, 3, 2, 1, n minus 1 factorial. Yes, here is also we are getting n minus 1 factorial. Gamma n is n minus 1 factorial. The obtained result you see that here, after one stage, we are getting gamma n in the term is n minus 1 factorial. The next thing is depends on that cos sx function n derivatives. N derivatives. So instead of moving that kind of complicated derivatives in integration and derivative, to move by simple way of gamma integral idea. The result is 0 to infinity e power minus ax x power n minus 1 dx equal to gamma n by s power a power n. Put a equal to is. That is the only thing you have to remember. A equal to is. Then expand and multiply by root of 2 pi pi. You can get the answer. It will be the idea of finding Fourier sine and cosine transform x power n minus 1. Previous problem also important. This problem is also important. Both the problems are important under sine and the cosine transform. Sine and cosine. Okay. Okay. I think all of you copied that problem scheme. Okay. That's all this session. And if you have any doubt, you can ask now. We will see some more additional problems in the next class, tomorrow class. Okay. Thank you. Thank you for attending this session.
Thank you, sir.
Thank you. Thank you.